So we welcome Wilfrid Kendall, who will address us on Google Maps and improper Poisson line processes.
Thank you very much. Good afternoon, everyone. I guess you could describe this topic as a kind of generic applied probability interested in spatial networks that might arise in transportation and communication. And I'm going to describe a stochastic geometric model that I've been working on for several years now and give an overview of how it works. And the good news is that during this, I'll be able to at least summarize some rather startling new results, which have really brought this to the end of the initial phase of investigation. That's the good news. The bad news is that it wasn't me that did the work. A very bright French guy called Jonas Kahn did this, and he's very kindly given me permission just to summarize what he did. But I'm going to start first by giving an overview and setting the scene. So, let me start by mentioning a couple of problems that you might think of if you're interested in thinking about spatial transportation networks in a very abstract way. The first is one that you could describe as, well, efficiency of construction. What's a good network? Well, if you delve into this, you find you're trying to meet competing criteria. Well known for at least 2,000 years, I'm sure the Roman emperors had this sort of problem. They built Roman roads, for example, across Britain with the objective of getting people very fast from one trouble spot to another. On the other hand, being Roman emperors, they were positively plagued all the time by budget worries. And yes, things haven't changed too much for some of us. And so they didn't want to build too many roads. Of course, they could, being emperors, pave the entire United Kingdom, as it was disunited then, with asphalt and march their troops up and down, but that would be very expensive because there would be the British weather to contend with, which would inevitably require constant expense in upgrading these. So the Roman emperors would have been puzzled as to what were good networks to design. On the other hand, very much more up to date, I myself have a small problem. I like to go on holiday from Coventry, where I live, right up to some beautiful spot in the Peak District. And obviously, Google Maps, or Bing, or Open Street Network will tell me how to get from one place to another, but I have some rather particular criteria which make this a complex optimization problem. I have to transport a cat. Those of you who've tried to transport a cat in a car know that roundabouts are suboptimal and small, windy roads are unspeakable, especially when you've just arrived. So roundabouts are an issue beginning, and small, windy roads an issue towards the end, and so we have to select our route extremely carefully. But the general thing is, the whole Google Maps Open Street Network Bing idea is you just supply your start route, start point, and your end point, and they do the rest. You could imagine, conceptually, there are all the possible places you might want to start from, and all the possible places you might want to go to, and they will form a kind of network over the region of interest. But all you do is you select your start point and your end point, and you get the route you want. So we started, me and David Aldous, looking at particular problems arising from David's interest in... Has he fallen asleep already?
I was young.
Yeah. I have a feeling I said something really stupid then, but I can't quite work out what it was. So David's being interested in these got me involved in thinking about networks like this and what constitutes efficiency for this and how you deal with the trade-off between networks involving a lot of connecting stuff, which is bad, versus networks which allow you on average to get quickly from one place to another, which is good. So here's an idealization of that first problem. You just consider a rectangle of size root n. That's a pretty good approximation to the United Kingdom. And you put down n cities, not randomly, just how you like, and you want to think about networks connecting them. And you measure their efficiency by minimizing the road length connecting all of the places you want to go to and from? Well, good choice, Steiner tree, if at least you can compute it. And then you want to measure the efficiency, well, by the average excess of the connection distance over the Euclidean connection distance, comparing the amount you travel on the road with the amount you travel as the crow flies. Clearly, you could maximize that by a complete planar graph between your destinations and sources, and that would be expensive in length. So, how do you trade off those two objectives? Directly competing against each other, a problem in frustrated optimization. So why not start with the Steiner tree? That's going to be very minimal in the amount of length it's used. By definition, it's the least length network connecting these cities. On the other hand, being a tree, it's probably going to be abominably bad at producing relatively short connections between different sites. So now, add a very sparse set of random lines. If you like, pretend that you're the government that's going to come into power in Britain in about a month and a bit's time, and you suddenly get lucky and have a lot of money to spend, so you just build motorways, and you build them more or less at random. This is not a political point. And to help matters, add a sparse rectilinear grid to make sure that the lines in the Steiner tree are connected, and maybe add some box structures to give you sort of ring roads around complicated bits. And the result we were able to show is economical with the connection stuff. It's going to be very close to if we use only a sparse set of random lines and a sparse rectilinear grid and not too many box structures. We're not going to use much more than the Steiner tree. And on the other hand, the average excess connection distance for large n is only going to be logarithmic in n. After we proved this, it occurred to me that people who built motorways have indeed been doing this sort of thing all along, and if you actually measure the distance from Coventry to Castleton using motorways, it's surprisingly close to the actual distance as the crow flies, even though one isn't going on a straight line route. There are some issues here. The original application was effectively to debunk a natural statistic for network efficiency, which is to consider the ratio of these two measurements, because such a very modest change to a network will produce a very efficient network as measured by this statistic, and one ought to try and do some better than this, and indeed Aldous and Shun have done so. Some other facts that we were able to establish: there's this logarithmic upper bound for the mean connection distance minus the Euclidean distance using the Poisson line process. Headings for this: there's a Steinhaus estimator for distance, a beautiful fact from stochastic geometry. If you've got a line in the plane which is regularizable, you can estimate its length just by throwing down random lines and counting the number of intersections those lines make with your curve. And that will end up in expectation being proportional to the length of the curve. Studying intersections of the original sparse Poisson line process and an independent copy, focusing on a certain Poisson line polygon, we get the logarithmic upper bound. It's actually of the correct order. You can show that if you are using geodesics, we actually in our arguments used approximate near geodesics. But if you're using genuine geodesics, then if you are using the lines from a Poisson line process, you will actually get an excess, as in bullet 1 there, which is of logarithmic order. And we can control fluctuations, bounding the variance of the excess connection distance. And also, indeed, and I'll talk about this next week in London, we can discuss statistics of flows on the network based upon this invariant line Poisson process. So that's all sort of 2008, 2011 stuff. Key role played by the Poisson line process. Just a bit of more conceptual discussion of what that's about. Poisson line process in Euclidean D space. How do you build it? How do you talk about it? Well, you essentially first start by thinking how you parameterize a line. And a line in d-dimensional space obviously has a direction which you're going to parameterize by a point on, quotes, a hemisphere, actually a projective space, because we're going to view lines, as it were, going in opposite directions as really having the same direction. Our lines will be undirected. And then you also need some measure of location of the line, which is essentially going to be a point on the hyperplane perpendicular to the direction of that line. So in fact, you've got some kind of twisted product of direction and location. The coordinate x is twisted by the direction because what plane, hyperplane it lies on depends on the direction. For measure theoretical considerations, that doesn't really matter, because the bit which makes this not an ordinary product actually has measure 0, and one can treat it very easily and essentially show that there is going to be up to positive multiple, an invariant measure upon the space of lines in d-dimensional space. There's a variant parameterization which simplifies things a bit by just replacing the x-coordinate, that funny twisted location whose ambient hyperplane depends on the direction, replacing it by the intersection of the line with some fixed reference hyperplane. And that works fine for all lines which are in directions not parallel to the hyperplane. But of course, in some generic sense, that's going to have measure 0, the set of lines parallel to the hyperplane, and so we don't have to worry about it. So once one knows how to represent lines in this way, by direction and by some measure of location perpendicular to the direction, then one can, for each line, assign a point in the representation space. One has an invariant measure on the representation space, and because one has an invariant measure, therefore one can produce a Poisson point process on the invariant space, and lo and behold, there you have a Poisson line process constructed by taking each of those points on the representing space. So, that's a brief discussion of random line processes. The secret in actually calculating with these is to try and argue as geometrically as you possibly can. Because if you don't, you have to do calculations, and then you have to get into the tricky coordinatizations of product spaces like this. Moving on to the second Google Maps example, we consider now how one might try to devise a model which corresponds to the Bing, Google, OpenStreetNetwork algorithms. Essentially, what you want to be able to do is you select a source and a destination point, and that will generate a route somehow, just like one might do on the web. And so we want to model a process in which, in which we input a set of nodes, x1 up to xn, and 2012, David suggested an axiomatic approach to this. What are the sort of things that you'd want as axioms here? Well, what you're going to get is a random network which connects the nodes which you put in. So, you make a list of your favorite holiday sites and your 3 homes from which you might come, and you immediately get a network connecting all of these. As a good modeling hypothesis, you might want this to be scale invariance. So under any Euclidean similarity, the distribution of the random network you get by scaling by the similarity should be the same as the distribution of the network you get by inputting the similarity applied to each of the nodes. So you want this to be translation invariant, you want it to be rotation invariant, but you also want it to have scale invariance. So when you do it on a small scale, you get essentially the same picture as on a big scale. That scale invariance is saying something which obviously breaks down at very small or very large scales, but seems not an unreasonable starting place if you're trying to think of a transportation network such as in the UK. We want to try and avoid some pathologies. In particular, it's going to be silly to just have all of the points in the network connected by straight lines to all of the other points. And the way we can eliminate that, whoops, I'm going too fast. This is a different pathology we want to eliminate. We want the length of the fastest route between 2 points to be of finite mean if it's a random network. And so let D1 be the length of the fastest route between 2 points at unit distance. We want that to have a finite moment. And then consider a network which is connecting points of an independent unit intensity Poisson line process. This is the other pathology that we want to exclude. We don't really want to think about networks which just go wild and connect these all by a complete graph. That will end up with, as the network extends, you'll start getting more and more connections, more and more lines. Everything will become very dense. So what you want is some constraint which says that when you've produced the network, in any unit area, you don't see very many lines passing through. Why don't you see very many lines passing through? Because points a long distance apart, which are coming past you, are going to be using the same sorts of routes as points which are very close together. So there's a sort of route reuse going on. So one puts in a constraint, something like this. I've written down the weak version of the Serson property, which is just that if you produce a unit Poisson point process over the whole plane and connect it up using this network production here, then you actually end up with a line network for which the average length per unit area is finite. There's a strong Serson property in which you say, don't look at all of the network. Look at that bit of the network which connects 2 points, but exclude, I'm saying this very badly, for every 2 points that you use, that you build the network with, exclude the parts of the path which are closer than unit distance to either the source or the destination. So in other words, only use the long distance part of the route for each of these. Now, do the same thing. Take a Poisson point process, connect them all up in that way, but now you're only looking at the bits of the path which are at least unit distance away from where you started and where you ended. So in some sense, the sort of the long distance part, and then you consider a point process which isn't unit intensity, but which is as intensity as large as you like. And the strong Serson property says then, if you take the limit of that, so you're essentially looking at points densely everywhere, but you're not looking at the bits of the routes close to the point as a start or the point as a finish, then you still end up with an average length which is finite per unit area. And then there's a weaker version of this, which is simply saying, even weaker than the Serson property, what you might call the pre-Serson property, is consider such a network and don't ask for the average length to be finite, just say that the particular network you get has finite length per unit area. So you don't get nests of routes which are somehow coming from all over the place and congregating around Birmingham or somewhere to produce an infinite density. So these are the axioms. David has shown some remarkable properties as a consequence. Just one example which appears to relate to an algorithmic phenomenon which people are using an empirical observation is that when you try and compute routes like this, you find that they all seem to go through a very small number, relatively small number of what they call portals, which are, as it were, where you switch from the small local transportation to getting the very long-range transportation. And one can empirically design algorithms, therefore, that do things efficiently just by connecting up these portals, and then every time someone proposes a start and a finish destination, you only have to do the work of getting quickly to a relevant portal and off at the other end. And one can see a phenomenon like this arising naturally from these Serson axioms. But of course, it's all very well to set down a list of axioms. Do we know that there are going to be any random structures which satisfy these properties? the institution I come from, notoriously, someone once wrote a thesis entirely about functions which were so regular that only the constants would suffice. You've got a question back there.
Yeah, sorry, I'm a little confused about your axioms, because it seems at the beginning you define the network for a finite set of nodes, but then property 3 is about an infinite set, so it doesn't seem to say anything about what happens to finite sets, unless you have some consistency assumption.
Yes, you need a consistency which I left out, which says that as you increase the number of nodes, you increase the network, or to put it another way, really what you're saying is between any 2 points, there is only one route that you're going to produce.
Okay. Thank you.
Right. Okay, so we need models for Serson. And because of the properties of Sersons, those models are going to be of interest in their own right. So the first one, you can read about in David's paper, and also Odus and Garnisan, is a hierarchical binary model. I'm not going to describe this very well, David, but you produce a lattice of fast connections and slightly slower connections and even slower connections and so forth. I'm not going to finish this. And you connect 2 points here by the fastest connection with some tie-breaking algorithm, because otherwise you can end up with potentially 2 different routes which are as close as possible. So you have some rule to say which these are going to be. Because this network goes on subdividing with even slower roads, in fact, each time you halve the road, each time you progress down to onto a lower scale, you reduce the speed even more, you end up with a connection between any point on the plane to any other point. It's not scale invariant, so you can use randomization to generate a rotated, shifted version which in algodic limits supplies something which satisfies the Serson axioms. And Aldous 2012 goes through the considerable amount of work to show that that works. That's one way to produce a Serson. Another conjectured way.
But in this construction, don't you have infinitely many paths in any unit area? Something is unclear. The last
You certainly have potentially infinitely many paths, yes. But we're talking about the fastest paths, and whereas any bit of this is clearly going to be on the fastest path between 2 points, they're likely, for slow paths, they're going to be really close together. And they're going to be excluded by that requirement that we only look at paths at distance exceeding 1 from start and end. I hope that helps sort of build up the kind of ecology of exactly what we're interested in here. Yeah?
There is a cost associated to each line like this when you say fast and slow. This is encoded in the line.
Yes, I forgot to say that. So to each line, you have a speed limit.
Right. Okay.
And that's it. You sort of fill in the rest yourself, can't you? So the alternative is a Poisson line process construction. There are various ways of describing this. The way I'm going to propose is that you consider a line process, but the lines you consider have to have speed limits of this kind attached. So to every line, which in the planar case is parameterized by r and theta, theta is the direction, r is the perpendicular as distance away from a fixed point. You also want a speed limit v. The invariant measure for the line process turns out to be a half dr d theta. The half is there because of aesthetic reasons. But supposing we want instead to parameterize lines with speed limit, these are going to be parameterized by v, r, and theta. And so we're going to look at points on a parameterizing space which have not just the perpendicular distance from the reference point and the direction of the line, but also its speed. So it's going to be a three-dimensional parameterizing space. I simply have to describe the measure on that space, then to be able to produce a Poisson process of that intensity, thus to be able to produce a network of lines to which I could do exactly the same thing as I've done for that dyadic network there, and just connect up points by saying they ought to follow paths and never break the speed limit. What's the right thing to put here? V to some power and again for aesthetic reasons, because it makes certain formulae later rather simpler, I'm going to put gamma to the -1 there, gamma -1 as a factor there. This is going to be a line process in VR theta space. If you just look at the lines and forget the speed limits, you'll find there are lines everywhere. It produces a dense network of lines. It's an improper line process. But if you remember what the speeds are, then it's a perfectly sensible marked line process. And for example, in this case, lines of speed greater than 1 are going to form a unit Poisson line process of this form. So essentially, by restricting yourself only to lines which are faster than a certain speed, you'll discover you've got an ordinary Poisson line process of intensity depending upon the speed. It's only when you get slow that this thing gets really improper. Okay. Now, is this a Serson? Let's just review the sorts of things that we needed. Yep.
Intensity be v to the minus gamma rather than v to the gamma?
Yep. Thank you. It's been a long term, and progressively towards the end of the term, I have been relying on my students to correct my minus signs and my twos and my halves, and I'm still in that habit. I apologize. Yes?
Still, you seem to say that it's only the slow roads which are dense, so do you assume some integrability of this? So gamma is bigger than 1? Or?
Yeah, I've omitted to say we need at least gamma greater than 1.
But in any case, the speeds are unlimited. Also in the hierarchical model, you do have infinite.
You can have very fast routes, but they are also going to be really rare. All right. So, where are the? Let's draw back to the conditions. What are we wanting? We want to be able to say that we can produce a network by selecting points and then connecting them up using paths which follow the Poisson line process but obey the speed limits. So, various questions. For any 2 points, is there such a path? The Poisson line process itself, clearly, although it's dense, is not going to go through every point. So how do you get onto the line process in the first place in finite time? That's going to constrain gamma. You want the lines not only to exist, but also to be unique. Well, at least almost surely unique. You can afford there to be occasional singular source-destination pairs for which there are more than one line, a cut-locus effect. But you want, if you pick 2 points a priori, there to be almost surely just one connection between the 2. You want the length of the fastest route between 2 lines to be finite. So the route is determined by finding out whether it is fastest amongst all possible routes. No reference made to actual length explicitly anyway. But it wouldn't do to have a construction such that the routes you were producing actually had infinite length, because it's actually the Euclidean length of the path that you're interested in. And what else? You want the Serson property. You want to show that if it's easiest to talk about the weak-Cerson property, you're producing a unit-independent Poisson point process of sources, destinations, and you connect all of those up. You want to find that the networks you're producing are reusing their paths in such a way that if you isolate any particular region, you only discover a finite length of path intersecting that region. So, this is just, I think, repeating essentially the discussion here, but in a higher than two-dimensional case. So you have each line marked with a positive speed limit, representing space has now v, r, and theta, or that funny omega-type construction if you're wanting a direction in higher dimensions. Here is the invariant measure which you use, which automatically achieves the scale invariance that we were acquiring because the choice of the functional dependence on v induces that. And what I said, the line process then is dense through the plane, or alternatively d space, but the lines of speed exceeding some threshold are going to form a proper Poisson line process, at least when gamma is, well, greater than d. No, I don't think I need greater than d yet. That shouldn't have been there. The first question is, can we get onto this network from an ordinary point? Or are we going to have to produce some unattractive construction where we're actually only connecting up points which happen to have been intersected by one of these Poisson lines? To do that, we've actually got to think about what we mean by a path. One notionally thinks that paths are going to be fairly easy. You just travel on one line, and then you travel on another line, and then so forth, and you just do a sequence of lines to go from one point to another. But that ain't necessarily so if you want to look at the fastest route connecting two points. Because you could end up with some odd limits where in order to get from point A to point B, they had to pass through point C, which could only be got to by passing through an infinite number of routes to get to C and then on. Bit of a question there. Could that happen? And it pays to take a more abstract approach to what one means by a path. Right. So we're seeking the shortest paths, what you might call temporal geodesics, or I shall describe them as pi geodesics, for a given line process pi of the form indicated here. We require gamma greater than 1. So the first thing to do, we introduce the maximum speed limit at any particular point. That's just for any point the speed of the fastest line passing through it. For most points that's going to be 0. But as soon as you're on the line process network, then that's going to be positive. It's going to be upper semi-continuous and random. Frankly, dealing with random upper semi-continuous functions is a horror and should never be done, but it's convenient to use that as a shorthand for saying at any particular point we define the speed at that point to be the appropriate supremum. Now we can talk about a pi path. Pi path is going to be a locally Lipschitz path. So it's going to have a notion at almost every point of velocity. It's going to integrate the measurable orientational field defined by pi. So for almost every point, the almost everywhere defined tangent of the Lipschitz path must belong to the Poisson line process. And moreover, it must obey the speed limit. So it's apparent that there are going to be such pi paths, because just any path that tracks along the network moving from one line to another line is going to obey these properties as long as you make it respect the speed limit. But it's also clear that there could be many other more complicated paths which somehow just keep borrowing appropriate directions from whatever line they're passing through in a potentially very disorderly fashion indeed. So what one can show from that is if gamma is greater than d, the underlying dimension, then you can show that if you look at a pi path and you look at the distance it travels in a fixed time, some fixed time t, there will be an a priori random bound, random because it depends upon the random process pi, of the distance travelled. So if you start at a point, if you look at the pi paths, these local Lipschitz paths obeying these properties, running for a certain time, they won't go further than a certain distance away from where you started. As a consequence, you can show the space of paths up to time t is closed, is weakly closed in the obvious Sobolev space, and then that the paths up to time t beginning in a compact set will together form a weakly compact set in the Sobolev space. And that's nice because it shows that if you can show paths exist at all, then there will be a way of taking limits of these paths to find a shortest time path, a pi geodesic. So as a consequence of this sequence of arguments, you can assert that pi geodesics exist, at least if pi paths themselves exist at all. So, nice so far, bit of abstract nonsense. Could easily be about nothing if in fact pi paths don't exist between two arbitrary points. However, turns out, at least if gamma greater than d, which turns out to be essential, you can always connect 2 points by a pi path. Let me describe the construction, which is categorically not of the form, well, you take this route and then that route and then the other route. It's more like if you went to the inhabitant of the village and asked for the quickest way to the nearest town, they'd say, well, what you really want to do is to get onto the A642, which doesn't go through the town and doesn't go through here. So now I'm going to tell you how to get onto the A642. What you really want to do is to travel from here on the A1010, which doesn't start here. So to get onto the A1010, and so they give you more details there, but they still haven't told you what to do at the other end, which is actually to take the A1042 and then some further more choices and so on. So they're telling you fastest path first. And then you build it up together into what potentially could be quite a tree-like construction if they were, I don't know, roadmap geeks and said, although you go on the 1010 to get to the 642, actually there are these few B roads that you can go on to move from one to the other which are much faster. And so you can see, even as you travel along the path, you could end up with clusters of infinite specifications of how to proceed faster. So here's how the construction goes. Construct small balls around your start and destination points. Connect the two balls by the fastest line that intersects both of them. Construct daughter nodes on that line which are closest to your start and destination. Recurse. Borel-Cantelli arguments establish the almost sure existence of a resulting path. And you end up with a binary representation of the path. And the note here is that I've always been talking about a two-dimensional construction. The construction itself can make sense in higher dimensions. I didn't say that there was going to be a fastest line from a ball around my start point to the daughter node. All I need to say is there is a fastest line around the ball around my start point to the ball around the daughter node and then recurse again. So actually in higher dimensions you're necessarily going to end up with a kind of binary tree representation of the path, where in order to go from any one place to any other place you have to actually, well, you might be able to travel along a line on one and a line on the other, but feature of the Poisson line process is in high dimensions these lines are not going to intersect, and so in order to pass from one to these lines to another you're going to have to do a similar construction like this involving intermediate lines, and in order to get from this line to an intermediate line you're going to have to do the same construction again and again and again and again. So in higher dimensions this is going to be intensely recursive, very much a binary tree representation. Nevertheless, one can show that the path will exist, you will get a finite time traversal, and actually a slightly more complicated argument shows that you can simultaneously construct paths between all possible pairs xi1, xi2 in RD. So it doesn't matter if the points lie on the line process or not. There are ways to get onto the line process in finite time so long as one has got gamma greater than d. Exercise for the reader is to try and visualize that in 3 dimensions, because essentially no path ever, no line ever connects with any other. So every time you want to change direction, you have to do that process of changing down gears, except that each time you change down 1 gear, you still have to do again that process of changing down gears, and there's an infinite regress. But the theorem is that nevertheless, you end up with these Lipschitz paths obeying the speed limit, which produce finite time connections. There's an illustration of the construction, at least in 2 dimensions. I haven't yet got around to producing a construction of the 3-dimensional path, probably in a movie rotating in space, so you can see the full complexity of it. And now, really, the star of this is Jonas Kahn, who took my estimates and pointed out that these would neatly go together to be summarizable in a simple inequality for what one might call the pi diameter, which is the largest time discrepancy between 2 points within a ball. So you take the supremum of the minimum times for pi paths to pass from some one point of the ball to some other point, varying over points, and we call that the pi diameter. And as a consequence of these estimates, you can show that the pi diameter itself must obey an exponential moment if raised to a suitable fractional power. This has been very, I don't know, the whole talk's waving hands, but it's been unvisual. I think I should show you some pictures of these pi geodesics. So I'm going to show you about 4 different pictures for varying levels of gamma so that you can see what sort of networks are produced when you try and do these pi paths. And what I'm going to do is I'm going to have a cloud of points here and a cloud of points over there, and I'm going to graph the geodesic connections between the points on the bottom left and the points on the top right. And we'll start with a small gamma. Gamma is 2.1, and you can see here that every one of these points is connected to every one of the points up there. But at this low gamma, there's very definitely a sense in which they all get from here to there by first joining these lines here, which are very much faster lines. There's a crude attempt at color coding. The darker the line, the faster you can travel along it. So there you see something which really does make it look as if this might have a certain property, because you're seeing this kind of funneling of all the many possible paths that start from here and go over to there into just 3 possibilities halfway between. As gamma increases, this attractive reduction into just a small number of paths starts to break down. So as gamma goes up to 4, you have rather more routes. Gamma 8, it's becoming more and more looking like a complete graph. Gamma is 16 is as high as I got with this. The construction I've done, of course, begs the question as to whether there are actually unique pi paths of shortest distance between this node and that node, for example. If there weren't, then this would be a misleading picture. So, are the geodesics unique? Fix attention on the planar case, gamma therefore greater than 2, and we want to be able to generate pi geodesics between fixed points, and in order to generate a network, we need to know that this pi geodesic is almost surely unique. So I'm going to look through the proof of this. It's actually the case that the way to prove this is first to prove a result which says if you have a geodesic, then this geodesic will only meet lines of pi in a direct line-meet-line way. That is to say, if you think of the pi path as essentially having its binary representation that I described, you want to know if there's a line of positive speed in the geodesic. The theorem says that there will be a line immediately before that and a line immediately after that in the binary representation of the pi geodesic. There won't be any of this business of going slower and slower and then faster and faster, not at any rate in the plane. In higher dimensions there would necessarily have to be. How does one prove this? Firstly, just by localizing, you can reduce to the case where L is the fastest line in the region with some fixed speed. You can then, for all lines in a neighborhood of the line you're interested in, start talking about the cost of the line. And high-cost lines are slow, and low-cost lines are fast, but this is designed in such a way that it's possible to reason with it and show that the pi geodesic will hit the line curly L, it will have to do so using some line of finite cost. And there are only finitely many finite cost lines, and therefore it will have to use one of them. It won't be able to work through an iteration of such lines which forms an infinite regress. Once we know this, it's possible to argue for uniqueness as follows. If I take all the pi geodesics between psi1 and psi2, they're made up of countable collections of intervals of the lines of pi. So fix a given line and consider the set of such intervals which lie in that line. If you consider two different finite collections of such intervals, and I should say these intervals defined by taking this line L and then looking at the way that pi chops it up. So there are going to be a dense number of points which are intersections of the rest of pi with L, and for each pair of such intersections you will have a different interval. So consider two different finite collections, each composed of non-overlapping intervals. There's a probability density argument. You can show that the total lengths of these two finite collections will have a joint density unless one is empty. Conditioning on the time that's spent off L, no two pi paths must have, almost surely two different pi paths using S1 and S2 respectively must have different travel times, because you've fixed the amount of time each of them spends off the line you're looking at. And if one of them intersects the line using S1 and one of them intersects the line using S2, because joint distribution of S1 and S2 lengths has a joint density, it follows that the two pi paths must have different total travel times. And because of that, one can show that if they're going to be pi geodesics at all, they must actually use the same finite collection of non-overlapping intervals. And that must be true for every line that you've got. And then finally, you can argue that you can reconstruct the pi geodesic uniquely once you know what are the collections of intervals that it uses from each of the lines in pi. So that's an argument which shows that uniqueness holds. So in fact, the graphs I showed you do work. They produce they're relevant, that you do indeed get unique pi geodesics almost surely between two fixed source and destination points. That's not, of course, to say that there aren't going to be source and destination points which are cut locus with respect to each other, where there will be several connections. Do these pi geodesics have finite length? I'm going to just skip through this, I think. There's an argument which shows they do, essentially using what you might call a racetrack construction. One can show that the length of geodesic in a fixed ball will be finite, The worry is, could you produce fast geodesics, which are fast because they go extremely fast, but a long way outside any balls? And you can bound the time spent by the geodesic above by looking at time spent on a racetrack construction around Xi2 and Xi1 using fastest lines. And upper bound the distance outside the ball by using the idealized path construction I've described. Yeah, I'm going to move over that and not spend too much time talking about that. I want to do two things now. First of all, I want to show you why it is that we get a pre-Serson, at least in 2 dimensions, for these constructions. So, an argument using Borel-Cantelli shows that you can find small perturbations of the diagram I'm about to draw at all length scales. And the diagram is as follows. You have lines which are very nearly forming a square of a large high speed c, a line very nearly bisecting this square of a slightly slower speed b, and then more lines here forming almost a square of speed a, which is smaller than b. Moreover, speed on this line is greater than 1, but otherwise, inside the large sphere, the large square, all speeds are less than 1. And then you can show, if you want to get from inside the small square to outside the large square, then if A, B, and C are chosen correctly, there's going to be only one way to do it. And the relevant set of inequalities are written down there. And what this shows is that if you've got a Poisson process over the whole plane and you're wanting to connect up every point to every other point, points of the Poisson process outside here connecting to points in here must go through this particular segment here. Even if the point of the Poisson process is up there, it's quicker for it to race round the circuit of the square to this point and cut across into here. And you can put that together to show then you have the pre-Serson property that says that if you take a Poisson point process and connect up all of the points using pi geodesics, you will end up with a diagram which only produces finite path length within any particular compact region. But that's now been superseded. So Jonas Kahn has now produced a proof, remarkably, of the strong Serson property, not just for all gamma greater than 2, but also for all dimensions d and gamma greater than d. Now that's a real surprise. I described those networks that you can produce in higher dimensions, which have essentially intrinsically binary representations for their paths, with lots of infinite passages down slower paths and then up again to faster paths in order to move across from one line to another. That seems like it would be impossible to produce the sort of Serson construction we're talking about, and impossible even to prove uniqueness. But nevertheless, it's true. The energy which is produced is that exponential inequality on the pi diameter, which I described before. And this can be used to show that the pi geodesics that you draw must make substantial reuse of shared lines. So just as an indication of what's going on, the argument is look at trying to cross from inside to outside of an annulus. If you get the radii tuned right, then you can show that this exponential inequality here forces any pi geodesic from inside going outside. It's got to make substantial use of a limited number of very fast lines transiting from inside to outside, because there's no other way it's going to be able to do it fast enough. So the exponential inequality, essentially applied, says you must get from here to here quickly, and the only way to do that is by spending a substantial amount of time on fast lines, faster than a certain amount, and there are only going to be finitely many of those, and then one can apply a measure theoretic version of the pigeonhole principle to say that essentially each of these pi geodesics is going to have to intersect with one of a finite set, and then the uniqueness result I've described shows that essentially you can control the amount of line used by the pi geodesics in this region, and thus eventually for the entire plane. And he also has some really clever arguments to show that uniqueness actually works in higher dimensions as well, and therefore the full Serson property is proved. So, moving to the time of conclusion, we've obtained scale invariant random metric spaces in RD, but visualizing this in dimensions higher than 2 is interesting to say the least. The improper line process construction actually delivers a Serson for finite points in the plane with gamma greater than 2, thanks to Kahn's results, and also remarkably in all dimensions for gamma greater than d. Still things that are left. Number of times I've talked about in dimension 2 what a pi geodesic looks like starting at one point and going to another, and I've noted in passing several times that we can't be sure that the pi geodesic might not at some intermediate stage slow down to a stop and then speed up again. It seems like that shouldn't work. I mean, why should a fastest possible path slow down and then speed up? I don't believe it can, but I can't prove it. So what's left? Can a pi geodesic ever come to a complete stop strictly between source and destination? For d greater than 2, certainly that's the case. It has to be in order to pass from one line to another. But in dimension 2, it feels like it oughtn't to be true, but I can't see how to prove it. Another obvious question links to Brownian maps, and I should mention the Kahn 2015 paper appeared this morning on the archive. So you can all go and read it. And he highlights a potential connection between Brownian maps and the Poisson line Serson with gamma equals 3, d equals 2. I don't think we believe that these can be the same. That's absurd. The question is, how different are they? And there appear to be a lot of similarities. Okay, they're just indicating reference. Yeah.
It seems that your networks, the parameter gamma, when it goes to infinity, your line, essentially metric looks like the Euclidean metric.
Yeah.
And when it goes to d,
2,
or 2,
if we're talking about the plane case.
sure, when it goes to 2, I don't know what it looks like, but do you have any sort of results that indicate that this might be like rigorously true rather than me wildly guessing?
I believe at one point I had an argument to say it went to the complete Euclidean case as d gamma goes to infinity, although I didn't find it very interesting, to be honest. I think what happens when gamma goes to 2 is really interesting. At gamma equals 2, you will not be able to get onto the network.
Mm-hmm.
So you would have to start and stop on the network itself. But once you're on, then you do have these finite connections. And that feels like it's an interesting critical case. But I don't know.
Other questions? So can you tell us any more about that Brownian map story?
Not really, because it's really Jonas's story rather than mine, but he's identified the Hausdorff dimension of the corresponding metric spaces as being the same.
Uh-huh. So you know the Hausdorff dimension of these guys?
Jonas knows.
This is in the new
Yes.
paper, isn't it?
Yeah, but he phrases it as it appears that
I
the
see.
Hausdorff dimension is. I suspect he actually knows how to compute it, but I thought it worth mentioning that was a potential connection.
I see.
Yeah.
Thank you. Any other questions? I'll say thanks again.